All right, so this video is about the most advanced worlds in this course and the climax really of all of our machine learning work. So this is a character recognition multi-layer neural network in JavaScript running in your web browser on Ancient Brain that you can clone and edit and modify. So it's a big project this, so let's take a look. We just start running it. Now, there's a lot of debug information here in the run header. But basically what's happening is in section 2 in the middle here, it's training. So there's a training image and the correct answer as to the classification of that training image. So in the notes, you see that this is using the MNIST database of thousands of images plus their classification. So it's training off that database, and we can see how it's doing with a demo. So the demo will appear in this section here. So what I'm going to do is demo a test image. So there's a 2, and it's classified it as a 2. Here we are. Let's try another one. It's a 9. It wasn't sure. Is it a 4 or a 9? 4 or a 9? It's not quite sure. There's a 4, and it knows it's a 4. So it's doing quite well. Now, you may say, these images come from here. Well, actually, they don't. These are a separate image collection to the ones in the middle. So it's never actually seen that image before. It's training entirely off the training images and not off the test images. So it's doing remarkably well. There's a 6 that it's never seen before, and it classifies it correctly as a 6. And remember, this network started off knowing absolutely nothing whatsoever. The weights were entirely random. It didn't know how to classify anything better than chance, which would be 10%, obviously, would be chance for 0 to 9. And it's got up to an accuracy of 90% here. Let's just reload and see how quick that accuracy changes from 10% up to 90% as learning goes on. So we just reload the whole thing. In fact, it was so quick, it's up to 50% accuracy already, because we've already done several thousand. It's that fast. Modern computers are amazing. We've already got through thousands of samples, and we've barely begun to look at the page. And this is running on a laptop. I mean, it's in the browser, in JavaScript. So you don't need assembly language. Assembly language would be faster, of course, but modern computers are extraordinary. It's not GPU assisted either, if you know what that means. All right, so it's up to 86% accuracy so quickly. The test image classified as a 1, 3 as a 3. Now, the real challenge is to actually draw it yourself. So that is the real challenge, and I don't expect this to work too well, at least not for a little while. So let's try and draw something. I draw a 1. Now, it doesn't have a clue what that is. Okay, so we'll clear that. Let's try a 2. Aha! It thinks it's a 2. How about that? Oh, or maybe a 3. But in fairness, that's pretty good. What you have here is a human being drawing something that it has never seen. The network has never seen me before. It's not even learning from my 1 or my 2 now. It only learns from these things here. So it's encountering a new handwriting that it has never seen, and it got 2 when the odds of getting that were 10 to 1. Oh, now it thinks it's a 3 or an 8. Let's see, does it do any better on a 3? We classify it as 3. Not bad, really. So as you carry on, you'll probably find the doodle will get up to about 60% accuracy, whereas the unseen images from the test set gets up to about 90% accuracy. And an interesting thing is why that is, because it hasn't seen these before either. So why are they so much better than the doodles? There's something going on there. So that's the glass half empty approach. The glass half full approach is just amazing that a machine can start from nothing, from total randomness, and be able to recognize, it's not doing so well with the 6, and be able to recognize any human writing at all. Oh, not doing so well there either. How about a 0? Oh, this is really bad. Let's go back to the 3 again. Okay, 3 is good. It knows that's a 3. So one of the things in the exercise and the big challenge here is, can we improve section 1 and make it more like section 3? All right, I've let it run a bit longer, and let's see, are our doodles any better? I may regret doing a 0. Oh no, a 0. It couldn't handle my 0 earlier, but now it can. So I think it's making progress. In my experience, it gets up to about 60%. And remember, 60% recognition may seem a bit weak, but random is 10%. So this machine is a hell of a lot better than random. All right, let's have a look at the code. And as before, I'm going to clone and edit. So first of all, the dimensions of the images come from the database, so we're not going to change those. They're 28 by 28. The architecture of the network is fairly up for grabs, not just the number of hidden units, and that's something you could consider changing, but also the way the inputs are done. So the way the inputs are done here is to basically end up with pixel squared inputs, 28 by 28, and the kind of spatial nature of the image is lost, as we discuss in the notes, as we explain a bit further in the notes. So it's not the ideal way of inputting an image. A better way would be to use a convolutional neural network. But it's remarkable how well this does, even with such a very simple way of inputting the image into the network. There are 10 output nodes, and they generate numbers, and the highest value is our guess. And we saw there with the doodle, it was worth looking at the second guess because the doodle recognition was so often wrong. Sometimes the second guess would be right. So our debug information showed the second guess as well, and you can see in the code where that's done. One thing you might like to modify in the exercise is what we do per step, how much training we do, how much testing we do. Now, I want to show you the setup function. The setup function loads 3.js libraries, and then it's able to construct the neural network. The MNIST library is the one that I want to talk about. There's the matrix and the neural network. The MNIST library does the fetching of that enormous database, and it fetches it into JavaScript, into the browser, and loads it into a massive object, which is called MNIST. So that's a global variable that you can look at in the console. And that comes by calling load MNIST. So let's look in mnist.js, which you can find. There's the address of it. I think you get to know Ancient Brain at this point. You can find where that is. It's in the uploads for coding train. So mnist.js is in here. And there's our load MNIST function. And it's been edited to point to the database, which is in uploads coding train. So there's 4 files here. And there they are. And 2 of them are huge and 2 are small. So basically the images are huge and the labels, which is just the classification, the images are tiny. So these are just text, basically. The classification 0 to 9 of the images, but all those images, there's tens of thousands of images, are contained within, there's the training set of images and the test set. So these come from the MNIST site where the formats are explained, but you don't need to know that. It's all been solved for you here. But basically all those images are bundled into those 2 files, which are then loaded into the JavaScript. Isn't it amazing how quickly it happens? It really is. That's a 47 megabyte file. And it just happens that quickly when we run it, that all those images load up. All right, so as you see in the notes, this world was started off by Daniel Schiffman and heavily modified by me. And a lot of the problem was to read in all this data. And one of the problems I had with Ancient Brain is that this is just kind of random binary data. That's the way the MNIST people do it. I think they made their database in a world before JSON and so on. So what I did was a bit of a hack. I made an exception for this binary data and allow it on Ancient Brain. So if you were using a neural network to do classification, do a machine learning on a huge database, you'd really need to have it in some format like JSON. You can't upload arbitrary binary data because there's all sorts of problems if the site would allow that. So hopefully for whatever database you want to use neural networks for, you can get your data into JSON, or if it is in some binary format like this, you can just write a script to convert it to JSON, and then you're good. Then you can upload it to Ancient Brain and off you go. All right, so now we're going to look at the exercise. So there's a lot of things you can do with this. I think one of the first things would be to look at the database. So mnist is the global variable that holds all the data once it comes in off the database. So if I run this and get into the console and I type in mnist, then I get, this is actually the entire database of images. So here we are. There are 60,000 training images and 10,000 test images. Just unbelievable how quick this all happens. So if we look at the training images, we can explore them. Let's look at the first 10,000 of them, and then maybe the first 100 of them. And okay, we can look at the first 100. So there's the first 100 of them, and there's the first one. So you can see what these images are. They're basically 28 by 28 pixels, very simple images. And we can collapse and expand these things here. Back in the editor, your next step might be to just look at how images are made out of the database. So that database, that array, how that actually manages to construct P5 images on the canvas. So have a look through that. Then another function to look at is how the inputs to the neural network are constructed from an entry in that array. So there are probably two of the things to get clear. First of all, the display element, and then the input to the neural network element. And it shows how our training exemplars can be all sorts of things. Audio, an image, all sorts of data. And provided that we're getting feedback as to what the correct class is, we can learn a mapping between that strange input space and the output space, and maybe that mapping will be a lot better than chance when applied to new inputs that we haven't seen before, and that is what we're seeing with this network. Now this exercise is pretty hard, so I'm actually going to make a change here just to kind of show you a bit more as to what's going on. I better close that, it's running away there in the background. If I change train to 0, and I just comment that out there, then what that means is the network is never trained. It never changes. So the network will be random. Actually, we'll put it back at 30. I run it, and the network goes, and it's already at 50%, 60% accuracy. It doesn't look random at all, but that's because this all happened so fast. We've already done 4,000 exemplars. So let's set train per step to 0. And then the network will never change. So if I save and run, aha! So you see what's happening? The score is 10%. 10% is random. 0 to 9, which is it? It's getting it right 1 time in 10, which is exactly what you'd expect with random. So it's not changing in any way, and we're just getting a random result. Set it to be 1, and then it will train, but very slowly. So let's run. And now we see it starts at 10%. So even with 1, the computer's so fast. We'll have to insert delays to slow this thing down, because look how quickly it's at 50% accuracy, and it's done 700 exemplars already. It's just so fast. One way of slowing it down is to increase the number of tests per step. So I think at this point I'll leave you to carry on with that. You can have lots of tests per step and hardly any training, and then the thing will improve, but much slower. So you can see what's happening. Couple other things. Increase the number of hidden nodes. Now, generally, hidden nodes, especially with a complex function like this, are pretty good. We want hidden nodes, but we want a fair few. But because that makes the network able to represent more complex functions, all other things being equal, but lots of hidden nodes means lots of calculations per step, means slower learning, and you can increase this to 6,000 if you like, but see what happens. I don't think it will actually improve it. If you reduce it down to 6, well, there's very little calculations needed per time step, but the network is then very crude and can only represent a crude function from input to output. So 64 good? To be honest, who knows? Experiment with the number of hidden nodes. Again, you can experiment with the weights, set them to a wider range, make them all equal again, and satisfy yourself that that does not work, and realize why that does not work if all the weights are equal. All they have to be is different, that's all, and the network works. If they're all the same, the network does not work. It can't learn properly. And why that is something important to understand. All right, and now for the big challenge, which is improve the doodle recognition up at the top. Improve the recognition here, well, that's not a very good one, but, and we've, this is not going to get anywhere, is it? Because we've got so little training going on, it's going to take ages to get up to 90%. So let's go back and we'll fix our training runs, train per step. We'll fix that back to 30, and that should be a bit better. So now we're hopping up nicely. We should be hitting 80 soon enough. Now it's heading up towards 90%. We can start thinking about doodles, but they only really seem to get accurate when this hits about 95%. So we may have to wait a while before trying out the doodles. How about the 3? It often knows what a 3 is. So there we go. 3 seems to work out quite well for some reason. It really agrees with this network architecture. Now, there is a change here. If you look at the lengthy video where Schiffman originally designed version 1 of this network, the doodles were sharp. So a change that I've introduced is to make the doodles a bit more like the test images here by deliberately blurring them. So I've done a blur, and in the code you can change both the thickness of the doodle and the amount of blur that it has. And I'm not really sure this has made a huge difference, to be honest. They certainly look more like the images that it's doing well on. So it's doing great on these test images, 0, 0. It does 90% on these images, and as I say, eventually gets up to about 60% on these. So the big challenge of this exercise is to make the doodle recognition better. So can you work with the thickness, with the blur, with some kind of manipulation of that image before you send it in to the inputs? All right, so to help you in your pursuit of better doodle recognition, I've put in a debug function here called show inputs. And what this does is it shows the entire inputs to the network for any given use of the network. So whether we're sending a doodle into it or whether we're sending a test exemplar into the network, this gives you a nice display where in the console. It gives you a display in the console of what the inputs are, and it shows the pixels laid out row by row. Now, when you do show inputs on the blurred doodle and the training exemplars, they look very similar. It's really hard to see what the difference is, but you can't argue with the fact that the network does much better at recognizing these than it does at recognizing these. So why that is the big open question of this exercise, and what I'd like you to make some progress on. All right, so I'll give you a lot of help in the exercise section as to how you could improve doodle recognition, and I'm hoping for some original ideas. If you look in NN.js, you can see the activation function is the sigmoid function. That's the one we're using. Shall we just take a look in here? And we just, oh, we won't find it in here, of course. We're going to find it in the same file. There we go. The activation function is the sigmoid function. But you can change the activation function to be tanh there, or you could use the rectifier function, which is discussed in the course notes, in the course pages. So it may be that changing the activation function would be the secret ingredient that would give us doodle recognition. It could be manipulating the images. It could be various other things that you might imagine, such as shifting the image about, moving it spatially in XY space. So it really is an open exercise. Can you get better than 60%? Can you get 80% doodle recognition? It's a tough problem. And of course, this is a real problem. It's great. It's, you know, this network is actually useful.